This week we're talking about robotic space missions. There's lots of kinds of robotic spacecraft. Does anyone know what these are? Can anyone name any of them at all? Curiosity? Okay, good. Sputnik, perfect. What's that one? What's important about that? Right, yep. Voyager, perfect. Good, good. And what's interesting about Voyager? Correct, yep.
It's also going at like 30-something thousand.
Yep. It's actually not the fastest anymore. The fastest is New Horizons, which is a Pluto mission. But it used to be. That's right. Any others? What's this one? Anyone know? This is on Mars. This is in 1976. It's called Viking. It's the first lander we ever had on Mars. This one over here is Messenger, that's orbiting Mercury right now. And that one is called Stardust. Actually, it was to collect samples from a comet wake. There's lots of kinds of robotic missions you can have. A sample return is a really interesting one where you actually go and bring samples back to Earth. Have we ever done sample return missions before? Okay, what's an example of a sample return mission? Yeah, so there was a Russian one actually that brought regolith back from the moon as a sample return.
Yeah, wasn't that like the one that you showed about the comet one? Is like the comet like dust to collect trailing?
Yep, exactly. So we've done that from a comet as well, and there's at least one more that I can think of. There was a Japanese mission called Hayabusa, which means peregrine falcon, which went to an asteroid and collected Itokawa, the asteroid Itokawa, which collected samples from the asteroid. They had an impactor, which hit the asteroid and got some dust coming off, and it went into a collection chamber, and then it sent the samples back to Earth with it. But a really interesting one would be on Mars, because we don't actually have any samples from Mars except for the little pieces of Mars that actually hit Earth, which happens a lot. There's rover missions, of course, Curiosity, Spirit, Opportunity, Pathfinder, a lot of other rover missions. There was some rover missions on the moon that most people don't know about, which were Russian ones, Lunokhod. Orbiters means it goes in orbit around a planet or a location, a world, and takes photographs and other kinds of measurements. We've had a lot of those around Mars. We've had some around the moon and other places as well. Cassini, which is that one up there, is an orbiter of Saturn. There's also flyby missions where you just fly right past something. That's like the New Horizons one. And the advantage of that is you don't need any extra energy to get into orbit. You can just fly right past it. So the early easy space missions are usually flybys. Yep. That's right. So that's an example of a probe. So Cassini had Huygens lander, which actually landed on Titan. So it detached a small portion of the spacecraft as a little lander, which was a European mission, which went into the atmosphere of Titan and sent us back pictures and measurements from within the clouds of Titan. So this is what the subsystems of the satellite look like. These are all the components. This is a block diagram. I'm going to go into more detail about different parts of it, but this is an overview of every piece of the spacecraft and what it does. Can anyone pick out anything interesting about it, or what do you think some of those blocks do? So this is a very interesting question. The first thing that we've noticed is that there's two sets of everything, or almost everything has two sets. It's called redundancy, and you want to make sure on a spacecraft that you basically do have two complete sets of everything. So if anything breaks along the chain, you have a backup, because you can't exactly go and fix something. So almost every spacecraft is designed in this way, that they have at least two sets of everything. There are certain systems that you can't necessarily back up. What's a good example of that? Okay, so the payload, there's only one payload, but actually even the payload itself is redundant in some ways. Is there anything at all that's not redundant that there isn't two of? Well, there's not two launch adapters. But basically, if you don't have a part that's really reliable, you want two sets of everything. It's called two strings, actually. And usually you want it set up so that, say this power distribution module breaks, you can just use this one, and then you can power the entire set of everything else. So it's not just like two separate spacecraft contained. It's reroutable so that you can have one part of the entire chain break and then use that part of the other chain. Yep.
What's the passive thermal control?
Yeah, so passive thermal control is a box there that just really represents insulation and shielding and things like that. So it's not really an electronic system. Most of these are electronic or mechanical systems, but that one, well, I guess it's sort of a passive mechanical system. It really just represents the insulating materials and the fact that you consider that as well.
There's only one battery.
Why? Oh, okay. So that's a very good question. There's only one battery. The reason for that is the battery is very heavy, so you don't want to carry two sets of batteries. However, the battery actually does have redundancy within the battery. So the battery has strings. It has, I think, 4 strings of 3 cells. And within the battery itself, you can have failures of some of those strings or some of those cells, and the battery still may have enough power to power the spacecraft. Anything else that we notice on the top level? So it's color-coded. The pink is power. What's the blue? I guess there's light blue and dark blue. What's the dark blue? Communications, okay. What's the light blue? Probably can't tell, it's hard to tell. It's because the thing about engineering, especially aerospace engineering, is everything is TLAs, 3-letter acronyms. So it's hard to tell what things are, unless you're familiar with the lingo. So I'll give you a hint. The C stands for something that these do. Well, they do control the payload. You can see where they're attached. Okay, the C stands for computer. So they're onboard computers. I don't know why they're not just called computers, but they're onboard. So, well, some of the computing is down on the ground, and you transmit the information, right? So you can send it commands from the ground, or you can have the spacecraft actually figure things out on its own with its computer. Now, the computers are about the power of your cell phone computer. So you don't need a whole lot. It depends. What is the purple? Can anyone guess what the purple is? There are sensors within it. Yeah, in fact, many of those are sensors, but their sensors are for a specific purpose. A sensor just means something that senses something, gathers information. What do you think that they're for? Okay, there's magnets, and we can measure the sun. So why would we want to do that?
Is it for like positioning?
Yes, exactly. It's for attitude control and positioning. It's so this satellite can sense where it is relative to sunlight, so that gives it a direction. And what might you do with a magnet?
Like electromagnetic fields that are given off by like planets and stuff.
Aha. So Earth has a magnetic field. So this can actually sense where it is relative to the Earth. And so these are sensors. Rate sensors are turning, like how fast it's turning or how fast it's moving. Rate sensors and magnetometers and sun sensors are all used to determine position and attitude. So attitude means like which way it's facing, right? Which way it's pointing. And the reaction wheels and the magnetorquers are used to change its attitude. Right? Well, we're going to talk more detail about that. And yellow, GPS. There's active thermal control. You can see, we're going to talk in more detail about this. This is payload, all of this, payload module. Okay. So power system. So how does this power system work?
The solar panels and the battery give energy to the battery charge regulator.
Okay.
And that's distributed.
Okay. So, right, exactly. So why do you need a battery at all? Why can't you just use solar panels if the solar panels gather energy from the sun?
Solar panels fail, that's a big issue because we get low cost power.
Okay, so if the solar panels fail, though, you won't be able to charge your battery, right? So you can't just use a battery.
Because you're not always going to be facing the sun.
Okay, you could always face the sun, actually, in this mission. That is sometimes a consideration when you have a telescope or something that needs to point a particular direction to take pictures or whatever. But this satellite actually could face in any direction. So it could always face the sun.
Well, like the satellite's not going to always be using the same amount of power that the solar panels are generating.
Right. Okay, that's definitely part of it. Yep. but there's something kind of big that even if it's facing the sun, there might be something in the way.
Oh, like something in the way.
Uh-huh. Something between the satellite and the sun. Like, so this satellite goes around Earth. So sometimes it's in the shadow of Earth, so it can't see the sun. So basically, it's called the night side and the day side. And when it's in the day, when it's facing the sun, it charges up the battery. And then when it's in the darkness behind the Earth, it uses the battery to power things. So it can maintain a steady flow of energy by charging up the battery from the sunlight. And then when it goes behind the Earth, it can still use it. That's right. Power systems, radiothermal generators, that is basically isotope decay. You can put some plutonium and use the heat from that plutonium to generate power. And really far space missions like Voyager and Cassini and Galileo and what's the Mariner, they all used these ones. And why did they use a radiothermal generator instead of a solar panel? Yeah, I don't know if they use the excess heat, but that's a possibility. But you're right. So it provides sometimes a stronger source of power. And the key thing there you said is it doesn't need the sun. Basically, if you're flying really far from the sunlight becomes less intense and you get less power from it. So you can really only use solar panels up to around the asteroid belt. Anything further out, and it's too far for solar panels to really be effective. So if you're sending a distant space mission, then you want something that doesn't need the sun. Sometimes actually our landers on Mars, I think Curiosity actually has an RTG as well, and that's so it can operate in night conditions. It can get more power at night. The Martian night is about the same length as the Earth night. 24 and a half hours is the day length. So yeah, you want to have a reliable source of power without having to access the sun. Also, things like dust storms on Mars might block out the sunlight, so you want to be able to get power anyway. What system is this? Subsystem is this? Communications. So what do things do here? And this is also the onboard computer. What do you think this is here? What do you think these are?
Radiation.
Okay, they look like old school things on your TV a little bit, rabbit ears. They're antennas, right? So how does a radio work? So you basically oscillate a magnetic field along a coil. A coil can be a specific length too, it could be a straight line. And so if you oscillate it back and forth, like power, if you put power back and forth on a coil, it generates a magnetic field. So it induces magnetic waves in not only the air, but in a vacuum or anywhere, right? So if you put power back and forth rapidly on a conductor, it induces a magnetic field. And the speed at which you do that you oscillate a current back and forth on a conductor, is the frequency of the radio wave. So you do it, many kilohertz or megahertz. So you do it millions of times per second. And the way we do this is there's crystals you can actually gyrate at, if you feed them voltages, you can get crystals to gyrate at specific rates. They just vibrate. And so you can actually use that to generate an oscillating electrical signal along a conductor, which induces a magnetic wave. So that's how it basically works. And what you have to do is use a transmitter. So the transmitter actually generates the signal, and the antenna is the coil that creates the magnetic field. So the transmitter provides the power and provides the signal to the antenna. And it's very much the same in the case of a receiver antenna. So it works the same way, but instead of generating that magnetic field in the air, it actually senses the magnetic field in the air, and that induces a current in the conductor. So when you're receiving, it's exactly the opposite. And so the magnetic field in the, I'm going to use the word air, but it's sometimes just space, induces a current that oscillates, and the receiver is able to measure that. Right? And so that's how you receive radio communications. You have transmitters that send those signals to create the magnetic fields, you have receivers that measure those signals, and that's how you receive radio waves. Sometimes you have a combined one that's called a transceiver, so transmitter-receiver. Basically, it sends those signals to the communications node, which can propagate the signal to where it needs to go in the spacecraft. Do you have a question?
Why is there a baseball?
Oh, that's a switch, actually. So it means that you can have it connected. You can have this transmitter connected to this antenna, or you can switch it and have it connected to the other antenna. Yeah. Do you know what? So you see the antennas are labeled. There's actually an antenna on the top and an antenna on the bottom. Nadir and zenith. Do you guys know what those words mean? So if it's pointing towards the Earth, that is nadir. So nadir is down. It means down, really. And zenith means top. So that means the one pointed away from the Earth. And why do you think you might have to have two? No, you actually have a one that sends signals and receives signals of each on the top and bottom. Why would you have to have two, though? One on the top, one on the bottom?
It gets turned. It gets
Yeah, exactly. It's really for safety. So if it turns, you always want it to be able to receive and send signals in any orientation, because sometimes it'll tumble and change its attitude. So yeah, and sometimes you want it to change its attitude. Exactly right. So we talked about this a little bit. You have different frequencies, and we're talking radio waves. So megahertz, kilohertz, those kinds of things. Light is just the same thing as radio, except it's much higher. And we have particular sensors called eyes that detect this, but it's really no different fundamentally from radio waves or microwaves or ultraviolet or gamma rays or anything like that. We just have this really narrow band that we can detect. So it's almost like we can see these magnetic waves in the air, but only in a very narrow band. And it's not fundamentally impossible for there to be sensory organs that detect like radio. You can imagine on some planet, maybe some organism can actually see radio waves, right? They're not fundamentally different. We just think of them differently because we've evolved to use this useful source of information, which is light. Because there's a lot of visible light, so we have sensors that have evolved to pick up this spectrum. Okay, so this is a relative size. So radio waves are long, like the size of buildings, and visible light is like the size of little microbes. That's the wavelength. And the wavelength is inversely proportional to the frequency. Okay, computers. You guys know how computers work, basically, but take in the communication information, take messages from the ground, and determine what to do and tell other systems what to do. So it's just really a distribution of information. Okay, so we talked about this system. Actually, there's two here. Let's talk about this first because it's pretty simple. What is this, that little green box?
Separation switch pack and launch it after, so maybe like once it reaches the space to like separate it.
Yes, exactly. So this rides on a rocket up into space, and then it has to separate from the rocket because it's actually bolted right down. How do you think it separates? How is it attached? It's bolted on. That's a hint. So how do you actually get it to separate? Like, do you think it's levers or some kind of ropes or what's that? Yeah. So you have bolts, explosive bolts. So the bolts actually have charges within them. And you trigger, that's what the separation switch pack is, you actually trigger the bolts to explode. They just break, actually. There's a little explosion within them that breaks the bolt in half. So, and why do you use something like that instead of using like levers and... Yeah, so it's reliable, it's light, it's the easiest way to make sure nothing goes wrong. Yeah.
What if like one or two of the bolts are duds?
Yeah, so they all have multiple, yeah, they're actually redundant within the bolt, so each bolt has multiple triggers. Yeah.
But if like one of them alone somehow wasn't moved with it?
In the case of the satellite, I think so, yes. And that would be a big problem, and you'd probably lose your satellite that way. In fact, I'm positive that satellites have been lost that way by not being able to separate. So what happens is the rocket goes up, brings the satellite, and then they're supposed to break off and just stay in orbit, right? And then the rocket body, the upper stage, the top of the rocket, goes back down. Well, sometimes it doesn't. It depends on its orbit. Sometimes it goes down and burns up in the atmosphere, and sometimes it stays in orbit. Either way, it's probably really bad for the satellite if it can't detach. But there are explosive bolts that they also use to hold down rockets, like the space shuttle was held down by bolts that were explosive bolts. And if a couple of them didn't release, it would actually have enough power to just rip them off, as long as most of them were gone. But not in this case. Okay, so this is what? What is all this stuff? Yep. So it's called the Attitude Determination and Control System, or ADCS, because it determines the attitude with the sun sensors and the magnetometers and the rate sensors, and then it can adjust the attitude using reaction wheels and magnetorquers. What do you think reaction wheels and magnetorquers are? Anyone have a guess? So magnetorquers are kind of like magnetometers, but it's like a sensor versus an actuator. So it actually uses a magnet. It's like a bar magnet that it can align in a certain way that will actually, the magnetic field will actually turn it in a particular way. So it can cause it to be aligned with the Earth's magnetic field. So it actually uses the Earth's magnetic field to turn itself. And you can turn them on and off, and this is how it works, because if you put an electric field through the magnet, you can actually activate the system, or you can deactivate it depending on where you want to use the magnet or not, right? And a reaction wheel is a gyroscope. Do you guys know what a gyroscope is? Yeah, so it's basically something that's rigid in space because it spins really fast, so it has a lot of angular momentum. And if it turns in a particular way, it tends to want to stabilize itself. And so it holds, and by speeding it up or slowing it down, you can actually cause changes in attitude as well. Then it has GPS, which you guys know from your car and your phone and stuff. And so it can actually use those because the GPS satellites are much higher. So this satellite is lower and it can actually receive the GPS signals just like it was on Earth. And active thermal control is just heaters. And passive thermal control is just insulation. Okay, so it has to launch and then it separates. So this is how it gets to space. This is a picture of how the attitude control system works. It has reaction wheels, magnetometers, GPS antenna, sun sensors, thrusters. In some cases, that spacecraft does not actually have any propulsion, but this one does. And it is able to do 3 axes of motion. So roll motions, that's the attitude. Roll, pitch, and yaw. And some satellites and some spacecraft have engines. There's ion engines, which work with an electric field, which generates a magnetic field, which accelerates particles really, really, really fast. So it's super efficient, but doesn't have a lot of thrust. But it doesn't use very much fuel, so it can run for long periods of time. Or rocket engines, which have an oxidizer and fuel, and it mixes them together in a combustion chamber and basically creates an explosion, which accelerates the spacecraft in the opposite direction.